And thank you very much for organizing this seminar. I greatly have enjoyed my collaboration with SEM over the last, what is it, 6, 7, 8 years or more beyond. And so today I want to give an introduction to the Reactive F method and just maybe some of the most important points I just want to highlight, and then give an overview of some new directions that we are pursuing in that particular domain. So there's contributions from various past and current students and postdoc in my group, and I'll reiterate their names when we get to their particular sections. So this is a somewhat recent picture of my research group at Penn State. So we have essentially all of them are working on reactive force field in some way or form, but there's a pretty wide range of topics that we're focusing on. Battery interface has been a relatively central item. We also have we've been involved in 2D materials like Maxines and 2D chalcogen like lithium disulfide and similar materials quite heavily over the last couple of years. And there's some new sort of areas coming up, things like machine learning, ferroelectrics and all that. So I'll give a relatively brief overview of these things and then look for some new developments, especially in the development of Reactive F, essentially Reactive F with a limited explicit electronic degree of freedom. Also, so this is another way that we communicate especially extensively with SCM, is through my company, ReaxFF Consulting, which provides essentially force field development services for academic and industrial clients. And so we have a very good connection with SCM in that particular form. And so providing essentially force field development capabilities. So essentially ReaxFF provides a relatively fast way to develop new reactive force fields. All right, so reactive force fields are essentially in the sort of higher computational tool. They're sitting essentially on top of quantum mechanics methods. Clearly, quantum mechanics methods are arguably the most fundamentally correct and also the most accurate of the atomistic scale tools that we have available. Unfortunately, they are computationally quite expensive. You need very significant computational resources to run them, and you cannot really go to very large systems or long time scales. So one step above there, we have the so-called force field-based methods, where essentially do not try to solve Schrödinger equation with approximations anymore, but we use a set of different functional forms that are faster to solve, but are clearly not as fundamentally correct as the quantum mechanical methods. And as such, since they are empirical, they need to be trained. And quite often we go back to quantum mechanics to provide that type of training data. If you want to do reactive molecular dynamics, then you have a couple of options. You can clearly stay within quantum mechanics. You do ab initio-based molecular dynamics, and that becomes a more and more popular choice now that with the computational facilities that we have available, and also the improvement in the quantum methods as far as their speed is concerned. You can also then try to make quantum mechanics faster, so that gets you into the realm of so-called semi-empirical methods, and in particular relevance here might be the sort of the tight binding methods that have really taken a very significant development over the last 5 to 10 years, and providing now indeed a means to run ab initio-based molecular dynamics with getting close towards hundreds of picoseconds of dynamics. Another option is to try to make the force field methods that have been around for a while, try to make them essentially, give them the capability to do reactions. And so the first effort in that particular field was done by Thursov and Brenner in the late 1980s, early 90s, when they developed the Thursov-Brenner and the Aribo potentials. So they essentially, these used the sort of a bond order concept, allowing bonds to make and break during molecular dynamic simulations. And this is sometimes in the field called the first generation reactive force fields. And this was followed by a second generation reactive force fields that essentially also included non-bonded interactions and polarizable charges and other types of more sophisticated functional forms. And so this includes the MEEM method by Baskins and co-workers, the COMB methods, and by Susan Sinnott and her collaborators. And then Reactive F falls in that particular category as well. Now, recently, over the last 3, 4 years or so, another option has begun to emerge in this particular area, which are essentially neural network-based potentials, so machine learning-based potentials that don't have a fixed functional form, but that have indeed a capability to run both non-reactive and reactive based molecular dynamics. And so there's sort of I'm pretty excited about potential connections between the physics-based reactive force fields like Reactive F and the neural network-based potentials. I believe there's a strong area of collaboration between those two domains. So Reactive F is based on a bond order concept, so that it shares with the first generation force field. So the central equation is here in the center, is by no means the only equation, but this essentially links interatomic distances Rij to a bond order concept. And so the bond order concept is something that we know pretty well from chemistry. So we have, a single bond in ethane, a double bond in ethylene, a triple bond in acetylene. What we assume is now that there's a relationship, a continuous relationship between bond order, bond length, and bond order. And so this is an empirical relation, clearly. So there's a bunch of parameters in there that we can train. But what we can now do is we can update these bond orders every iteration so that we can smoothly break existing bonds and recognize new bonds. Now, if we want to use free-body terms like valence angles or four-body terms like dihedrals or similar things, we make them bond order dependent. So we multiply them all by a bond order. So when a bond order goes to 0, all other connectivity-dependent interactions go to 0 as well. On top of that, we put non-bonded interactions. Now, this is somewhat unique. So this is really where you make the hard choices when you design a new force field reactive force field concept. In Reactive F, we chose to calculate non-bonded interaction between every atom pair without a sort of a switching function. So that means that actually every bond doesn't only contain a bond order-based term, but it also has a Coulomb stability. So especially if you have a bond between atoms that have a very different electronegativity, you have a very significant Coulomb part, and even going to ionic bonds like sodium chloride are in Reactive F almost exclusively based on Coulomb interactions. And so this then is combined with a polarizable charge distribution, mostly using still the EEM method. I'll talk a little bit more about that. So this is essentially a method that uses electronegativity differences to calculate geometry-dependent charges, and these are updated every step. And that combines pretty well with Coulomb interaction, so that actually gave Reactive F a significant amount of transferability, because we can use it for covalent materials where the bond orders are pretty much describing the bond stability, but it also can work for ionic materials and essentially mixtures between them. So what we do essentially in Reactive F, we have atom positions, and then things kind of split up. We have an area that's based on bond orders. So we calculate the bond orders, we correct them. I'll talk a little bit about that bond order correction later in my presentation. Then we find angles and torsions, we calculate all those energies, that goes in the system energy. And then there's a completely separate track where we calculate charges, so that's done with the EEM method. We get a Coulomb energy, and we get a van der Waals energy, and they come back. And as you see, there's no communication between charges and bond orders, and that limits some of the applications of Reactive F. And towards the end of my talk, I'll talk about the Reactive F method, where you essentially allow for some communication between the charge domain and the bond order domain. So we get a bunch of energy contributions, if you see here. We sum them up, and that gives us a system energy, and we can get forces, and then we can do pretty much normal molecular network simulations. So why we do that is clearly our aim is we try to get Reactive F to be as close to quantum mechanics as we can. We typically use DFT as our training. We can also train Reactive F is necessary against post-DFT method or post-Hartree-Fock method like Cobalt cluster, but most of the time, because of computational resources, DFT is still our main sort of fitting tool. So we try to get it as close as DFT as we can. And when we do that, we can essentially get a very significant speed up. So this is a somewhat older figure, but for 400 atom system, we get about 1 million times speed up. And also Reactive F scales almost linear, while most quantum methods scale much, much worse than linear. So the bigger the system gets, the better this comparison typically becomes. What this allows us to do very comfortably more than 1,000 atoms, and actually there's significant literature of using Reactive F to 10,000 to 1 million atoms. The world record Reactive F simulation is roughly 500 million atoms right now. That requires significant resources, but the bottom line is you can do very, very significant size simulations. So looking more at the central equation for a second. So this is that bond order bond distance relationship. Well, then this is not the only equation. I'll show the full Reactive F equation in a couple of slides. One thing that really distinguishes Reactive F from many other reactive force fields is that this bond order is very long range. So this is the carbon-carbon picture that we have here. We see that even at 2 angstrom, we still have half of a bond order left. And that gives reactor a chance to get transition states right, because most of the important transition states for hydrocarbon chemistry happen at carbon-carbon distance of roughly about 2 angstrom. If you completely get to your bond order of 0 by 2 angstrom, which is what the first generation bond order potentials typically did, then all you can do is just completely break a bond and make a new bond. So all your reaction barriers are going to be pretty much the strength of a carbon-carbon bond, which is something like 80 or 90 kcal. Many important reactions and for hydrocarbons have actually much lower barriers because they're concerted reaction. When you break a bond, you essentially make a new bond at the same time. And so this long-range bond order relationship gives Reactive F a chance to actually capture those transition states. Then we couple this to a sense of, so Reactive F doesn't have explicit electrons, but it has many sort of implicit electron terms. One thing that it does is it counts the amount of valence electrons. So for example, carbon gets given 4 valence electrons, so methane is stable, no corrections needed. Also the methyl radical is okay, there's no correction needed, but it clearly has 1 extra valence electron, so it can easily make an additional bond at essentially no cost. But if carbon tries to make 5 bonds, then essentially it gets a penalty for that. We just sum the bond orders around the carbon. If it goes over 4, then essentially we get a sort of a positive energy. We don't completely avoid this 5 member, so it can maybe sometimes be an important transition state, especially for not so much for carbon, but let's say for silicon can actually over-coordinate much easier than carbon. So this is something that you actually can actively train against. But the bottom line is that we can essentially use this atom energy to make sure that species like CH5 or CH6 are not overly stable. Now, one important thing that we have to do in Reactive F is, so we have this long-range bond order relationship, and that's nice for transition states and all that. One of the disadvantages is that the next atom, so we see here a nice sort of 0.95 bond order between the carbon atoms, so that's close to a bond order of 1, so that works well. But also the next neighbor is close enough that we still get a quite significant bond order, like this 0.10 bond order between the carbon and the next neighbor hydrogen. And that's clearly physically incorrect. There's no real bonding interaction with carbon and hydrogen. There's really no electron density between them. So this should be purely repulsive. And so what to deal with this, we essentially go for sort of a one-step correction scheme. We only use that for covalent materials, but we really need to get rid of those 0.1 bond orders. And so we do this with this set of equations, somewhat complex, but they're pretty much a sort of a filter. And they are dependent on the amount of over-coordination of the carbon. If the carbon is normally coordinated, let's look at this 4.1 case, so with a total bond order of close to 4, then those weak bond orders get significantly reduced, so they go down by a factor 10, while the strong bond orders get retained. So the idea is that the strong bond, if carbon is normally coordinated, it should only really be interested in making strong bonds, and all those weak bonds orders should essentially be filtered out. However, if carbon becomes a radical, so look at the 3.5 case, so then essentially those those weak bond orders can remain. So a radical carbon can indeed make these sort of longer range weak bond order relationships that, for example, can be related to hydrogen transfer within the hydrocarbon. And so this is pretty much a sort of a cleanup concept. So this is what we have on the left, our uncorrected bond orders. Once we correct them, we get a much better physical picture. So those 0.1 bond orders have gone down by a factor 10, and now they don't provide too much attraction. So now that the van der Waals repulsion and the angular repulsion, angle strain can pretty much take care of any attraction there. But my strong bond orders are almost the same in strength. So the 0.95 only went down by a very small amount. So this works really well, and it removed those unrealistic bond orders and leaves the strong bond orders intact. The disadvantage is that computational expense increases quite significantly, because now all my bond orders go from being a two-body function to a multi-body function, and bond orders are used everywhere in Reactive F, so this is fairly expensive. We already do this for covalent systems. For metals, we really don't have to do this, because for metals, they naturally like to, they're typically so electron rich, they like to make those long-range bond orders. But for covalent systems, this is a pretty important correction to make. So on top of that, we have a charge calculation scheme. So we use the electronegativity equilibration method by Motier et al., which is very similar to the QEQ method from Warpé and Goddard. And so every iteration, we calculate charges. You solve this, essentially this relationship where we have for every atom the electronegativity chi and the hardness eta. And that essentially is the energy that it takes to polarize the molecule. And then energy that we get back from the polarization is the Coulomb attraction. So that's essentially this term here. We take the derivatives and kind of optimize the charges based on this. And so that is a relatively expensive step because we have to solve essentially an NBM matrix. But with some computational tricks, we can make that almost go linear with time. But this is still the step in Reactive F that takes the most computational expense for large systems. So every iteration we update the charges, and that essentially allows us to give us a reasonable physical response, especially when the carbon changes. For example, a carbon atom changes its chemical environment, going from an oxygen-rich to a hydrogen-rich environment. It changes its charges automatically, and so that allows us to essentially take that sort of chemical change into consideration. So this is the full Reactive F functional form, and clearly I'm not going to go also here. This is that bond order part. You see that this is a pretty complex form, and that's nice to some extent. So that helps Reactive F in its transferability. The disadvantages. This is our first of all, it is a complex form. So Reactive F is significantly slower by roughly a factor of 50. Compared to most non-reactive force fields, which have a much simpler functional form. But also, since it is so complex, there's almost certainly a better set of functional form, but finding it is pretty difficult because changing a functional form takes a fair amount of refitting, but also you have to rewrite the code. And so these type of functional forms really survive for much, much longer than they probably should. I mean, Reactive F is roughly 20 years old. There have been some efforts to improve the functional form here and there, but nothing too consistent. So this is really an area where I hope that maybe a connection between Reactive F and some of the neural network-based potentials can be helpful. We can, for example, do this thing that we take some of the Reactive F functional form and then get rid of the React 3 and 4 body function and see if the neural network-based or machine learning potentials can kind of fill in these type of things and maybe lead us to suggestions for other types of functional forms in a faster way. Okay, so one of the big focal points of Reactive F is its ability to get transition states right, and especially for these type of concerted reactions, which are arguably the most important reactions at low temperature, meaning sort of room temperature to almost 1500 Kelvin or so. So in the concerted reaction, a bond is broken and is made at the same time. And this is pretty spectacular. This is a trick that, for example, enzymes use to break and make peptides and all that. The CN bond in peptide is pretty strong, about 80 to 90 kcal, but somehow an enzyme managed to break these bonds up with a barrier of about 20 kcal, making it a room temperature event. And they do this quite often by maneuvering water molecules in the right place and do the trick that you see over here. We have 4 water molecules. The OH bond is pretty strong, 125 kcal, 5 eV or so. But you see that this reaction where I essentially modify 4 water molecules, do a concerted proton transfer, only has a barrier of 20 kcal. So this is essentially a room temperature event, roughly. And Reactive F reproduces that quite well. And it can do that because it has this long-range bond order. So even when we are at the transition state, we still have nice, the total bond order is conserved because we have these half bond orders. So instead of having bond order of 1 and 0, we get a whole bunch of bond orders of close to 0.5. And so that means indeed the total energy that we need is relatively low. This also works in condensed phase materials. Here's, for example, a picture for oxygen vacancy migration in barium titanate. Kind of the same deal in Reactive F. So Reactive F can actually, these metal oxygen bonds are pretty strong, probably worth about 80 to 100 kcal. These oxygen vacancy migrations can happen at a barrier of only 80 kcal or so. So that's once again a room temperature event. And Reactive F can reproduce that because of its long-range bond order. So when we are in the transition state, we still have significant bond orders available. So once again, we do this because of the speed up. Our aim is to try to get Reactive F to be as close as quantum mechanics. Typically, once again, it's DFT, but we can, if needed, go beyond DFT in our training. We also can train directly against experimental data if we need it. but most of the time, to get a decent training set, we have to go to quantum. It scales much better than quantum-based methods. It's almost linear, while most DFT methods scale n to the power 3 and maybe worse sometimes. But it is significantly slower than non-reactive force fields, so a factor 50 or even a factor 100 compared to EEM-style potentials. And that actually means there's a significant amount of room for example, hybrid Reactive F, non-reactive force field simulations, where we use the advantage of the non-reactive force field speed with some of the local reactivity of Reactive F. So we've been working on this over the years, and we found out that this functional form is very, very flexible and transferable. So we managed to take it successfully across the periodic table. So we can describe it for ionic materials, covalent materials, and lots of materials that are kind of in between, like, for example, transition metal oxides, transition metal carbides. They can be quite successfully being described as a combination between covalent and ionic materials. So we have been actively distributing the code. It has been supported by open source and by commercial software, in particular by the AMS Reactive F, providing a very efficient. AMS is certainly currently the fastest implementation of Reactive F that I'm familiar with, and it provides a very nice user-friendly Reactive F simulation environment. Another thing that's really developing quite nicely is essentially, and it's also supported by the latest AMS implementations, at least most of these options are supported, is essentially accelerated molecular dynamics. This is still, so we can essentially, Reactive F by itself can get you to the nanosecond scale, 10 to 50 nanoseconds, depending how long you're willing to run your simulation. But if you put accelerated or hyperdynamics tools on top of that, you can quite often get to a sort of a microsecond time scale, clearly depending on how amenable your system is to an acceleration. Parallel replica dynamics essentially allows you, for systems with a localized barrier, to parallelize time. So with Reactive F, we managed to get ourselves to a microsecond of time with that thing. Parallel tempering allows you run the same simulation at different temperatures. You exchange between the temperature images, so you get essentially a thermodynamically feasible way to use temperature acceleration. You can also change your energy landscape by increasing the energy of your product and reactant states, but keeping the transition state roughly at the same time, so making the transition state essentially more accessible. CVHD is a nice recent implementation in that particular domain that has shown to work quite well for accelerating, especially gas phase reactions. And then we have things like hybrids between Monte Carlo and molecular dynamics. Particular nice example is the application by Knights & co-workers of force bias Monte Carlo connected with Reactive F, where we essentially managed to grow these very nice looking carbon nanotubes, which are typically the type of carbon nanotubes you might see at about 50 or 100 microseconds of simulation, which is clearly not accessible by straight molecular dynamics. But by combining the sort of advantage of Monte Carlo, allowing us to take bigger time steps, we can essentially get to these type of structures. Tracking options is something that we recently implemented and also now supported by AMS, where if we know the transition state quite well, we can essentially find a pre-transition state and then use a local boost to get across the transition state. It's particularly useful for things like polymerization reactions. So let me show a sort of a small example of a recent Reactive F project. So Wenbo Zhu, a student of my group, he recently graduated in the last fall. He worked on chemical looping combustion, essentially using copper as using a copper oxide redox couple to essentially activate fuels. The idea is that if you don't want to use, if you use air, then we have nitrogen in there. Nitrogen can lead to NOx chemistry. So instead of using air as an oxidant, we want to use a metal oxide like copper oxide. Copper oxide is chemically not incredibly stable, so it's a pretty good oxidant for hydrocarbons. And on the other side, we can essentially use the copper metal to enrich biomolecules. We can, for example, use molecules like with a high oxygen content and use those to oxidize the copper. So we go back to our copper oxide. We essentially get a fuel that essentially is less oxygen rich. So this is essentially easier to use in our regular combustion cycles. And by sort of switching between the combustion and the sort of reduction and oxidation, we can essentially get a sort of a chemical looping going on. So to do that, we developed a Reax description. So we started but we were kind of focused on C1 chemistry, so our main training set was focused on C1 cases, but we found actually it transcends reasonably well to larger hydrocarbons. So we trained Reactive F against DFT for binding energies on different surfaces. And then we take a couple of key reactions. So here's, for example, carbon monoxide or hydrogen monoxide bound on the surface, recombining into CHO. So we very much focused on carbon monoxide-based chemistry here. And we see that in most cases, we produce the DFT barriers within about 4 or 5 kcal. Sometimes we are a bit off in the reactant, because as long as the reaction is downhill, we didn't necessarily, we focus more on the transition states than on the reactant case, but we can probably get these things a little better if we focus a bit more on the reactant chemistry. But overall, so this is just a fraction of the training set. Overall, we found pretty good agreement with, especially with barriers for these type of conversion reactions. Then we do a sort of a small scale validation case. So we looked at the methoxy radical is a key intermediate in many sort of biomolecule transitions. It's clearly, in the gas phase, it's pretty unstable, but it can actually have a relatively long life expectancy on a surface, because it can get stabilized by binding to a metal surface. And so we started with a methoxy radical, and we checked out these various chemical reactions we saw, and we found that there are quite good agreement with the data from experimental work. So the nice thing about these radicals, they convert pretty quickly. So this is, we ran this at 1400 Kelvin, and we see that these things convert quite fast. We can even go to lower temperatures, probably, if we really want to connect better with experiment. But 1400 Kelvin gave us a nice sort of balance between chemical reactivity speed and at least not that far from the chemical temperature window. We cannot go much higher than that, because at some stage, clearly, my copper surface is going to melt, and then my reactivity is going to change significantly. Then, after we established the force to work pretty well, we could, for example, try it out for different aspects of the biomolecule work. So we take, for example, various glucose configurations or carbohydrate configurations, and check out the reaction kinetics. And so there we found, for example, that the open chain glucose has a much faster reactivity than the closed chain. And that partly is because the open chain glucose can land 2 hydroxides on the surface at once, and then dissociate at the same time, making essentially a local double bond. That's much harder to do with the closed chain glucose, because it's hard to get that configuration right. So you can very quickly see what is essentially the reactive difference. Also, we see that indeed that we indeed can successfully oxidize the copper. So we start at the oxidation state of 0, and during the reaction, we essentially end up with an oxidation state between 1 and 2. So copper clearly has multiple stable oxidation states, and so we see indeed that we can make a copper oxide during the simulation. And then we can do the reverse of that one as well. We can start with a copper oxide, and essentially, for example, here we check it out for various hydrocarbons. Not surprisingly, methane is the least reactive of the hydrocarbons, but it's very interesting to see, for example, that normal butane is significantly more reactive than isobutane. So we can really see how the configuration of the hydrocarbon changes its reaction kinetics. And in this particular case, we see indeed that we get a reverse. We start here with a high oxidation state of copper, and we go back to essentially, we don't get completely to metallic copper. It's also because of the duration of our simulation, and we get very much oxidation migration limited here, but we drop down to an oxidation state approaching 1 in this case. One thing that's really exciting here is that we can now connect the solid phase chemistry with the gas phase chemistry. So this is what our copper oxide. So we start with a pretty clean looking copper oxide particle, but we see that during the simulation, relatively quickly, the reaction becomes pretty much surface diffusion limited. So it's very much like how fast can the oxygen from the core of the particle make its way to the surface. And we see indeed that the shape of these particles is very complex, depending on temperature clearly. But if we look here at 800 Kelvin, we see that our core is still fairly crystalline, but the surface begins to take also the oxidation state. We also even see a sort of a hydroxide. So we get a mixture between different oxidation states. We get a hydroxide and an oxide, and the configuration of these are very complicated. So this provides us sort of a window into what actually these solid oxide catalysts or these solid catalysts do, and what the dynamical response is to the gas phase during the simulation. What's kind of interesting is also transferability. So we presented this work And we got emailed by Huang Jizang Lin from the Max Planck Institute. Say, well, I heard that you guys got a copper carbon oxygen force field. I would like to use this for these sort of, I do some work on carbon-based gears, and I look for for a way to put a sort of graphitic carbon on a copper support. So we sent this force field. Clearly, it wasn't trained for anything remotely similar to these type of gears, and it actually works pretty well out of the box. It doesn't always work. Sometimes, indeed, you know, the transferability is not infinite, but it shows that indeed these force fields can actually transfer pretty well between different applications. Okay, let me switch gears significantly now and just to sort of show some new developments. So one in particular that we're excited about is, so most of the work in the Reactive F right now is using essentially regular molecular dynamics. And we're trying to see if we can essentially improve some of the sampling of Reactive F using path integral methods. So Kartik Ganesham, who graduated last year from my group, has essentially been working in that domain. The idea is that light elements like hydrogen could have significant non-classical motion, essentially sort of partial tunneling types of behavior that you don't sample with regular molecular dynamics. In path integral molecular dynamics, we essentially we use multiple replicas. That clearly is takes some expense because each replica is essentially has the time of one of your regular MD simulation. But this allows us to essentially capture some of that non-classical behavior and essentially get some of the tunneling effects into there. So we used the thermostated ring polymer MD, and that essentially allows us with 10 beats to give a reasonably good approximation. So that means that our time goes up by a factor 10, but you still can do reasonably long range dynamics with that. So we use that for Maxine systems. Maxines are two-dimensional metal carbide with typically an oxygen cover. So this is the titanium carbide version of the Maxine. We can essentially use GCMC tools, which are supported within AMS. We can essentially put things like cations and water in the interlayer between the Maxine. And then we can run essentially path integral based molecular dynamics. So this is typically what we see during these simulations. And so one of the key things we look at is essentially change in the protonation state of the surface. So does the path integral molecular dynamics change the surface protonation kinetics? And the short answer is yes, it does. In PIMD, so we see here, this is the reaction that we have. So on the right side is essentially our surface proton. On the left side is the proton in the liquid. And we indeed see that in PIMD, the surface proton is significantly more accessible than in classical MD. For bulk reactions, it's a little bit less obvious, but if you look at it in a bit more detail, you see that my sort of transition state region, where the proton is really shared between the water and the H2O+, is a bit more accessible in PIMD compared to a classical MD. So indeed, our proton transfer rate, even in the bulk, is significantly higher in path integral MD compared to regular MD. And so you can indeed then see, if you just plot this as a sort of on a free energy curve, you can indeed see that the tunneling that we can sample better with path integral MD is significantly allows us to have a significantly lower effective barrier for proton transport. This is especially important for lithium. Lithium is itself a relatively light element, so we see that for sodium and potassium, it's a kind of a regular picture. Yeah, so all my proton-based barriers are lower, but the overall shape of the energy curve is somewhat similar. But for lithium, the entire shape is shifted because not only the proton is affected by the PIMD, but also lithium, because of its very low molecular mass, itself has actually a significant effect by the PIMD. And so between water molecules, we see the same thing. Now, this is kind of interesting. So if you have lithium in the water phase, we essentially don't see proton transfer in the classical. So the classical is completely missing here simply because there are so few proton transfer events around the lithium, because lithium made such a tight water shell that we simply couldn't even sample it with classical MD in our time scales. So the PIMD, we actually can sample it because of the better tunneling capability. You also see here for sodium and potassium, once we send the same picture of sodium and potassium, since they have a weaker coordinated water shell, we can sample the proton transfer even in the classical molecular dynamics. But we see indeed that with PIMD that my proton transfer is significantly faster. And so we can then see how that affects diffusion constants. And especially for the lithium case, we see that the diffusion constant changes very significantly by almost a factor 10 to the power 3. For sodium potassium, there's also an effect, but it's a more marginal effect. But especially for lithium, it is a very significant. So for without in the system, apart from lithium, it's sort of a factor 2 or thereabouts, or a little bit more. But for lithium, it's a much bigger change. Well, we feel that this might be an important thing to consider, especially lithium is clearly an ion of very significant interest to the battery community. And so these type of non-classical molecular dynamics tools may be quite important to simulate lithium migration. And it is a factor 10 in speed loss, but that still allows you to do relatively significant ND simulations on these type of simulations. Okay, switching topics one more time. So I want to talk a little bit about Reactive F. So this is the Reactive F concept where we actually have some sort of level of communication between the charge section and the covalent section. And this follows some of the concepts earlier developed in EFF in the Lewis force fields from the Goddard group. And so what we try to do here is have a communication channel here, and we do that by adding an explicit electron or hole. We primarily, Reactive F has mainly been using explicit electrons so far, and what we do is the electron is a charge carrier, but the presence of the electron changes the overcoordination term of the carbon. So when the carbon has an electron, its valency goes down to 3. Normally it has 4 valence electrons. When it captures an electron, its valency goes down to 3, so that clearly affects the stability of the bonds that it can make. And so, for example, a methyl anion, like we have here, would essentially try to break one of its carbon-hydrogen bonds because it only has 4 valence electrons, and so that weakens its CH bonds. So that's more or less the idea. Now, one thing that we had to do to make this work, we had to shift from EEM to AX2. One of the disadvantages of EEM is that it gives a non-physical long-range charge transfer. So if we couple that with these explicitly charged electrons, that essentially caused issues because half the electron charge would directly jump to the neighbors. In AX2, we can essentially resolve it. AX2 is a 2x2 matrix, but it actually is a relatively sparse matrix, and so it is not that much more expensive than EEM in that particular form, and it gives you the right sort of dissociation limit. So what we can do so Reactive F doesn't get electron affinities right. I mean, it believes that methane, for example, has a positive electron affinity, so the methane anion is more stable than the methyl itself. That's incorrect. Methane has a very strongly negative electron affinity, similar with water. So, but OH, for example, has a strong positive electron affinity because the OH minus is very stable. And so in Reactive F, we can capture these type of radical anion types for the species much better. And so our first attempt at this was published in 2016, where we managed to show that we could, for example, simulate electron transfer in polymers. This is essentially a aromatic part, conjugated part of the polymer with an aliphatic domain. And we see the explicit electron over time manage to jump and find the electron. So here on the right, we have a radical. And so it over time, it managed to jump across the aliphatic domain and get captured by the radical. And we directly compare this to Ehrenfest dynamics, so ab initio-based molecular dynamics, and found out that we can essentially train Reactive F to get the right timescales for these things. We can, for example, use this with water. So on the left is an explicit electron with water. It essentially just gets pretty much solvated. On the right, we have an OH radical, and during the simulation, we see that the electron gets captured by the radical, making an OH minus. And so we can really do this transition between OH radical and OH minus, which is hard to do in Reactive F. So Jamil Hossain, he graduated from a group last fall. He essentially managed to extend this to lithium graphene interfaces, where we can do this simulation. This is lithium cation. We have an electron-rich graphene. And during the simulation, an electron jumps from graphene to make a neutral lithium that can now essentially make a metal. We managed to train this against a wide range of data, including things like in-plane conduction and out-plane conduction for graphene, equations of state, and a wide range of curved and non-curved hydrocarbons. And then we tested it out for, this is a graphene anion, so there's all the electrons are the same, but we just give the location of one electron, indicating that these electrons are highly mobile, and over time they spread around over the entire graphene lattice. And if you look at graphite, we see indeed that the graphene, that the extra electron only localizes within one sheet. So its conduction in the plane is much higher than between the planes. We can do fancy things like adding defects, and we see that the extra electron really organizes itself around the defect. And we can do things like if it has an sp3 linker, we see that the sp3 linker really indeed works as a sort of a electron conduit. So over time, indeed, the electron can delocalize over two of the graphene sheets by transferring through the sp3 linker. So now we can start doing things like real sort of plating concepts. So we can have a start with lithium plus. We can add extra electrons to the graphene. These over time will migrate to the lithium. Lithium becomes lithium neutral, and the lithium neutral can now organize itself as a lithium metal on the surface. And so this is a simulation really hard to pull off in a physical way with Reactive F, because the EM already gives you automatically the charge transfer, and so you don't have a real electron transfer event. With Reactive F, we can essentially simulate this type of electron transfer event at the interface. An interesting new sort of concept there that we published last year, and it's done by Kate Penrod, who graduated last summer from my group, is essentially combining this with constrained DFT. So this is an acetophenone radical anion. So the excess electron can clearly delocalize itself over the molecule. With constrained DFT, we can essentially calculate the relative energies of the electron being at various positions. And we find that the electron likes to hang around over the carbons. It doesn't really like the oxygen terribly much, and it really hates being on the hydrogen. And so we can train Reactive F against that. And with that, then we can see at 300 Kelvin, so we can compare our equilibrium composition of the electron location. At 300 Kelvin, we don't match that well because Reactive F doesn't sample the kinetics fast enough to really move the electron around. But if we go to 1500 Kelvin, then the barriers for electron transfers are small enough that we can rapidly sample this. We see a very good agreement between the Reactive F composition and CDFT composition. And we can even draw a sort of an electron density map and compare that to some way of form with the type of electron density surfaces that we can get from DFT. And we indeed see reasonably good agreement that we see that the oxygen is not terribly accessible, and the electron really sort of spreads itself out fairly freely over the aromatic ring, but really doesn't get to this CH3. Atom 2 is not very accessible to the electron, and that's indeed what we also see in the DFT calculations. So this provides an interesting new tool to really train the sort of the internal electron motion in Reactive F. And clearly the electron is a classical species, but over time it starts behaving like a much more sort of a quantum picture. So it can really indeed sort of spread out its density of the molecule. So that brings me to the end of my presentation. So we have essentially a tool that can handle very complex chemistry and chemical diversity, lots of transferability. It has a low computational costs, especially when you use it in a parallel environment like the AMS code. You can scale it quite comfortably on about 10 cores to something like 100,000 atoms. And if you go a little bit bigger, you can get yourself to 1 million atoms. And so a recent extension to Reactive F allows us to actually evolve some limited aspects of electron transfer with Reactive F. We're kind of excited. We have recently expanded this to oxides. We hope to get more local better dipole calculation, which is important for ferroelectric response. But we also may be able to do some electrocatalytic effects. So that leaves me to thank the various sponsors over time, in particular the British Royal Society, who provided initial Reactive F funding when it was at Newcastle University. And I would be happy to discuss questions with you. Thank you very much.
Yes, thank you very much for this very interesting presentation. Lots of new and recent things. Yeah, so far there have been no questions in the chat yet, but maybe I kick off with one or two.
Sure.
So you mentioned in the beginning that yeah, you could in principle combine Reactive F with other more efficient force fields.
Sure.
Could you comment on the extent to which this has been explored? Like, can I do Reactive F with, say, embedded atom or so?
We haven't done embedded atom. I don't think that will be terribly hard to do. I mean, the communication is much easier. I mean, clearly there's examples from QMMM. Reactive F NM is going to be always easier. So we actually recently did a Reactive F OPLS hybrid. And that was actually relatively easy to put together because all you have to, the non-bonded communication is fairly straightforward because both methods use charges. You just have to have the fixed charges of OPLS to get into the EEM scheme. But also you just have to figure out where the shared bonds and shared angles and dihedrals are. And since both methods are fast enough, it's pretty easy to calculate them with both methods and then have some sort of rule for sharing that type of information. So we actually published last year a sort of a hybrid OPLS Reactive F concept where you actually can use machine learning to relatively quickly develop OPLS parameters for new chemistries, and then essentially have a easy to set up OPLS Reactive F interface. I think EEM should work pretty well because the EEM embedding concept mixes reasonably well with the Reactive F overcoordination concept.
Mm-hmm. Then, yeah, we have a first question. Just start from the first one here. Are there any general rules for building training sets? Are there structures, reactions that are recommended or that should be avoided, especially with respect to overfitting?
Yeah, that's a good question. It requires a longer answer than we have time for here, but I'd say I like to think get the charges in the right place first, and that's pretty easy to do because you can use fixed molecules for that just to get the charge parameter in the right ballpark, and then get all the basic bond energies right. That's also not that hard to do because you can typically use a set of relatively small molecules to get these in the right space, and then start opening up yourself toward the more complex things like transition states, solid phases, and all these type of things. And in the end, you have to be willing to also, I mean, you may use these molecular species as a sort of initial guidance, but make sure that if you are not, if you, for example, want to make a solid phase force field, you may want to sort of lower the weight of these type of molecular components during the fitting. So that's it is good. One of the tricks with these things is get your parameters in the right initial space, and then lots of training tools. There's some pretty good parameter training options available right now. Once you get a sort of a good set of initial parameters, they can pretty much take over from there. But the key trick is just to get your parameter, nudge them into the right area before you really start your training. If it's from the outset, you need to get a reasonable force field first, because if you, one of the problems with reactive force field, if you really get bad gases, your molecule will simply explode on you. And clearly, whatever, no matter how clever your training tool is, you can never train a force field against that.
Right. Yeah, something what I have been personally observing a little bit. Maybe you could comment on that. So there are different groups of parameters in React. So sometimes you see that basically they affect each other. Let's say on covalent interaction has an influence on bond orders or so. Can you comment on how would one approach this?
Yeah, that's actually one of the challenges with reactive force and property in general. I mean, with non-reactive force fields, the length scales are much more separate than in reactive force. I mean, reactive F any bonds, that's probably about 5 or 6 different energy terms that contribute to the bond stability, because there's a bond-valence angle coupling, you have the Coulomb interaction, you have van der Waals that's still active, you have your overcoordination. So it's not just one single energy term that defines the bond strength. And that means you get a much, much stronger parameter correlation. That makes your sampling a lot harder. But there's a lot of new development in that domain. I mean, there's genetic algorithm-based tools. I mean, we have some neural network-based tool that can get you that work better on that particular sampling. But you have to be willing to take a bunch of cycles there to really sample that particular parameter correlation. But it is true, indeed, that you cannot really say, oh, I'm going to take this parameter by itself and train it, and then all the other parameters are probably going to get affected with that. And that correlation makes the training set significantly harder.
Mm-hmm. Then a next question. Would it be possible to use ReaxFF for calculation of electron collision rates, E- collision rates? Would this be this would be very useful for plasma processes.
Yes, I think so. That's actually the interesting area that we're very interested in. Clearly, the E-reactive F electron is not a real electron, so you have to be somewhat cognizant of the limitations there. Another thing that you can do is treat the electrons in a more continuum fashion. So we, for example, are now working on electron beam interactions with surfaces where we don't have explicit electrons, but we just, we know where the electron beam is, and we can use relationships to figure out how the kinetic energy from the electron beam gets transferred to the nuclei. But yes, but one important thing is with E-reactive F that key species in plasmas, like indeed radical anions and these type of species, you can at least describe them with E-reactive F and give them the right energy. So that gives you a much better chemical handle on what might actually occur in your plasma. So I think, yes, I think that we've only scratched that surface in my group, but I do believe indeed that it has a much better plasma type of application. We actually are working on a project where we look at interactions of radiation with silica surface, where we actually use electrons and proton mixtures to generate water on silica surface. That actually works pretty well. So you can indeed see how the combination of electrons and protons can react with these surfaces, create water molecule. But you actually see indeed that electrons themselves are essential in that process. So yeah.
So the next question would then be about using the molecular gun to study ion irradiation in graphite.
Yeah.
And whether there is to what extent there is a training or retraining.
Yeah, we've done that. We published in 2016 by Unicor work. What you need to do is you need to have a very stiff inner wall, because typically the speeds of these things are significant. The normal Morse function in reactive F is too soft. But you have the option in reactive F to switch on a much stiffer inner wall repulsion, and you can train this. We train these things against what's the name of? We can train against DFT or other types sort of empirical functions. So you get that sort of inner wall repulsion, right? And then you can see juices. So we did that with helium, neon, krypton, and other type of normal metals and their cations. And that worked pretty well. So we actually saw that we could make defect structures that seemed to compare quite well to experimental defect structures.
Yeah, so indeed the next part of this question is, yeah, we will cover aspects of parameterization itself in a hand-on session. That should be the third session later on. So everyone who's interested in that, please tune in again. The following question is, I wanted to ask on how to properly add in the training set the salvation effects on homogeneous catalysts.
Yeah, at least in the React training so far, we simply have done this with explicit waters. We don't have a salvation model in Reactive F. That actually would be an interesting to add, but we just simply add explicit waters, and that clearly is expensive on the quantum side of things. But that works pretty well. So we can actually do, we can both have so Reactive F actually works pretty well for water autocatalytic events, where you can see how the presence of one or two water molecules can significantly lower the barriers for proton transfer events. But also can do salvation things. For example, if I take a sodium chloride pair, clearly in vacuum in Reactive F it will be stable, but if I indeed put water around it, it will pretty much auto-dissociate. So these type of effects work quite well.
Yeah, also, would it make sense to include a salvation model in itself? Because that to some extent might be more expensive than Reax, right?
Well, I don't know. I have to figure. I'm not a salvation model expert, to be completely honest. I could imagine that there will always be applications where that will be useful. I think one of the things that's nice is that it makes your communication with quantum easier. Because in quantum, clearly, you would like to use those salvation models because it makes just your life so much easier. And right now, you cannot actually train Reactive F against these type of implicit salvation models for quantum. So that might actually, for the training purpose, might be nice that you can directly have a sort of a implicit salvation quantum data into your training set. And there may be other applications where it could be helpful that you just have, you can maybe say, okay, I can use less water. Instead of using 10,000 water molecules, I can use 1,000 water molecules, and then the rest is a salvation model. In that way, it might actually be turn out to be cheaper.
That's it. Another question is there a direct relation between real temperature and the one used in MD simulation? If yes, can it be increased to accelerate the processes?
Yes.
So there will be the following session will exactly deal with aspects like this.
Yeah.
But I think also in your case, in your talk, you
Yeah.
briefly mentioned such things.
Yes. Now, increasing temperature is a dangerous game. Yeah, it can be done, but your entropy, you don't know what your entropy is going to do, because every reaction will be accelerated differently based on temperature. Pressure is a much cleaner acceleration tool. Even pressure is clearly there's limits to how far you can go with pressure, but pressure just essentially just linearly increase the amount of collisions. Temperature also clearly has entropy. So if I take, for example, a normal hydrocarbon, if we go to 2000 Kelvin, my pyrolysis is going to be extremely boring because it's all going to be ethylene. That's all you're going to get. Entropy tells you it's going to do that. And then you compare the experiment, it will be horrible because your experiment at 1000 Kelvin tells you, yes, you get some ethylene, but you also get much bigger hydrocarbons. So that entropy effect is something that you have to be really aware of if you use temperature acceleration. We do it, everybody does it, but you have to be aware that it is very nonlinear.
Well, there will be sound problems again. Yeah, so this should be picked up in the recording. Yep. Maybe that's the best way of coming back to this, Pascal. There's another question about the electron mass of one in ReaxFF. So you really give it the same mass as a proton?
Actually, we tried it out. You can also give it 1/10 of the mass of hydrogen. It works. Your time step has to be changed a little bit, but yeah, we use one because it's easy. But it indeed, you get lots of weird stuff. If you actually explicit electron with hydrogens, you get weird sort of electrons circling hydrogen. So the neutral hydrogen looks really weird in ReaxFF because it's really sort of since they have the equivalent mass, you don't get electrons around the nucleus, but you get them as sort of equivalent species, which clearly looks extremely weird. But we tried it with 1/10 of the hydrogen mass, and then at least that sort of picture looked better. It's really hard clearly to go to the real electron mass because I wouldn't know how to take a time step in that case.
Could ReaxFF model the interface reaction between a lithium transition metal oxide and electrolyte?
I believe so, yes. Especially if lithium stays positively charged, that's relatively easy if it stays the same oxidation state. Well, you have to train it, of course, but if it changes oxidation state, then maybe something like ReaxFF would be necessary. But I think on the cathode side, that picture is a little bit easier than on the anode side.
So that are all of the questions from the chat. Maybe Ole or Rosa have some.
Yeah, I have some. That was wonderful new results on the ReaxFF simulations. Just wonderful. The ones you showed with the graphene and the lithium and the electrons.
Thank you.
So I was wondering, were those run with AMS?
Yes, the graphene wings were run with AMS. The graphene simulation were run with AMS. Yes. Let's see. I think the Acetophenone was run with my standalone code, but I think that one should be able. It was so small that we could run it there. The graphene thing, indeed, especially actually interestingly, the graphene is actually pretty fast because it does. Since in that case, every atom has an extra electron, we don't even need to call AX2 anymore. So that actually runs pretty fast there.
Yes, it's wonderful, and I thought maybe, yeah, the time step and the electron you already mentioned. If you go too low, I was wondering if you can just plug in acceleration into ReaxFF2 if you feel like it, or if you see there's anything that would prevent such a thing.
Acceleration, sorry.
Yeah, and some acceleration techniques, let's say, I don't know, whatever flavor you want, if it's not parallel replica.
Yeah, sure. That should work. Absolutely, yes. And also, I think powerful integral would work really well because then you may be able to change the mass of the electron a bit, and you can really get a tunneling of the electron much better. Because now we're doing classical tunneling dynamics with electrons, which is clearly weird. Powerful integral might help us. We may even be able, if you give the electron a lower mass, maybe we even really targets its normal, the electron-related normal modes, and really puts the right amount of energy into them. So that could be very interesting.
Yeah, exciting. And one very brief one. And maybe you can comment on the training. If you compare ReaxFF training to ReaxFF training, how much more effort would it be?
Yeah, it's certainly not easier, by no means. It's really hard to put a number on it. I mean, the acetophenone radical thing, that was pretty easy because you have just a couple of well-defined. The graphene electron stuff, that was a pretty tough job.
Yeah, I can imagine.
Especially the in-plane. So the in-plane conduction, the in-plane versus out-plane conduction, that was something that we had to hit really, really hard. That was not something that came out of it by itself.
Okay, so yeah, thank you very much. Very nice.
There are two more questions by Anthony. Related to the increased pressure to accelerate the reaction, there is any relation between real and simulated pressures? For instance, the simulated P is 10% higher than real one, or something like that. And the second question is, what is the acceptable error between energy barriers calculated with ReaxFF and DFTB?
Yeah, the second is a hard one, because then you get to the question, what is the acceptable error in DFT in the first place? But yeah, it is really what you care about as the person that does the simulation. So an individual barrier you can get as accurate as you want. The trick is if you have a really large set of reaction network, it will be hard to get everything within 1/10 of a kcal. Now, I always go on the premise that the DFT barrier error is, what is it, 2, 3 kcal, whatever that number is. So I try to say, okay, if I'm within 2 kcal, I'm going to be pretty happy, because that's my DFT error about to start with. But if I, for example, know a barrier better, like for example, like the oxygen migration barrier I showed in my examples in barium titanate, that's a barrier we knew experimental evidence that indeed the DFT is pretty good for that one. So that one we really gave a lot of weight, because it's the most important barrier for these type of solid phase oxides. So there we really said, okay, let's get it within 0.1 kcal, because clearly if you have 1 kcal off, unfortunately that barrier is an exponent. So if you're 1 kcal off, then you can really get a significant slowdown of your reactions. And I think there's some pretty good, I forgot that publication, I'm afraid, but there's a recent publication that indeed shows that pressure is a very nice linear acceleration tool, provided clearly, you don't want to go into gigapascals of pressure, but if you do gas phase dynamics, if you stay at least in the gas phase realm, that your reaction increase is very nice and linear. So 10% increase in pressure does essentially increase your reaction kinetics by 10% as well.
Yeah, very interesting indeed.
I think that was Kai Leonard's group that published a paper on that, if I remember correctly, but my memory may not serve me completely correctly there.
I have a small question. Can you hear me?
Yes.
I have a small question on path integral. I was just curious about you showed that there's a big effect for water proton transfer with lithium, and maybe it's really obvious, but so you didn't use also beads for the lithium, I guess?
We use beads for lithium as well, I believe. I have to ask Kartik, but I believe we did, yes.
Okay, so that's, but there's a lot of lithium, right?
Yeah, well, there's about 10 or 20 lithium ions in there, so that's substantial, yeah.
Yeah, very impressive. Yeah. Okay, nice.
Good. Yeah, so if there are no further questions, yeah, I would like to thank Adri very much again. It's a great honor, and we're very, very delighted to have you. And yeah, thank you for the interesting presentations and yeah, the answers to all the questions that were emerging. Yeah, so to everyone else, I hope to be able to welcome you in the following sessions, and thank you very much for your interest in this new series. And yeah, with that, I would like to wish you a pleasant day.
Okay, thank you all very much, and thank you for organizing this. It was a great pleasure to participate.
Goodbye.
Bye, everybody.